On the morning of July 30th, 1908, the sky above central Siberia split open. What happened in the next few seconds would become one of the most significant cosmic events in recorded human history. In the remote Tunguska region, hundreds of kilometers from the nearest city, the taiga forest stretched endlessly in all directions. Birch trees, pine and larch covered the landscape as far as the eye could see. The morning was clear and cold, typical for a Siberian summer. Evenki herders moved through the forest with their reindeer. Trappers checked their lines. A handful of isolated trading posts marked the only human presence in this vast wilderness. Then the sky ignited. Witnesses reported a column of bluish-white light, as bright as the sun, moving rapidly across the northern horizon. The light was so intense that it cast shadows and was visible for hundreds of kilometers. Some observers reported feeling intense heat on their exposed skin despite being dozens of kilometers from the object's trajectory. Then came the impact. The explosion occurred approximately 8 kilometers above the ground, near the Podkamanaya Tunguska River. The energy released was catastrophic, estimated at between 10 and 15 megatons of TNT, roughly 500 times more powerful than the atomic bomb dropped on Hiroshima 37 years later. For context, this was the largest impact event in recorded modern history. The blast wave flattened approximately 80 million trees across more than 2,000 square kilometers of forest. The devastation was so complete that witnesses compared it to matchsticks scattered by a giant hand. The shock wave circled the Earth twice, recorded by barometric sensors as far away as England. Seismic stations across Eurasia registered what appeared to be an earthquake. For several nights following the event, the skies over Europe and Western Asia glowed with an unusual luminescence, bright enough that people reported being able to read newspapers outdoors at midnight in London. Yet despite the magnitude of the explosion, no crater was formed. This absence of an impact crater would become one of the event's most puzzling features, spawning decades of investigation and theories that ranged from the scientifically plausible to the wildly speculative. Semyon Semenov, a trader living approximately 60 kilometers from the epicenter, later provided one of the most detailed eyewitness accounts. His testimony, recorded years later by investigators, described the sky splitting in two, with fire appearing high and wide over the forest. He reported heat so intense that his shirt felt as though it might ignite. The sky then closed with a crash, and a shock wave threw him from the porch where he had been sitting. In nearby settlements, people spoke of a ball of fire crossing the sky, followed by a sound like artillery fire that shattered windows and knocked people to the ground. The Evenki people, indigenous inhabitants of the region who lived by hunting and herding reindeer, were the closest witnesses. Their oral traditions would preserve accounts of the event for generations. They spoke of the god Ogdi growing angry and sending down fire to destroy the forest. Some described their reindeer herds being scattered or killed by the heat. Others reported that the ground shook so violently they could not stand. Trees exploded into flames without being touched by fire. The sun itself seemed to fall from the sky. This was Tunguska, an event so powerful it would reshape scientific understanding of cosmic impacts, an explosion that occurred in one of Earth's most remote locations, ensuring that years would pass before anyone could investigate what had actually happened, and a mystery that, more than a century later, still holds lessons about humanity's vulnerability to forces beyond our control. To understand the Tunguska event and why it remained mysterious for so long, we must understand the world in which it occurred. In 1908, The Russian Empire was a land of profound contrasts, stretching across 11 time zones from the borders of Europe to the Pacific Ocean. Tsar Nicholas II, the last emperor of Russia, ruled an empire that was simultaneously medieval and modern. In the great cities, Moscow and St. Petersburg, electric lights were beginning to appear, and the wealthy discussed the latest scientific theories from Western Europe. But in the vast interior, particularly in Siberia, life had changed little in centuries. Villages had no electricity, no telephones, no roads connecting them to the outside world. News traveled by word of mouth, carried by traders and itinerant workers who moved between isolated settlements. Siberia itself was a world apart. The name derives from the Tatar word Sibir, meaning sleeping land. It was an accurate description. This vast territory, comprising roughly 77% of Russia's total land area, held only 7% of its population. Much of it was taiga, the great boreal forest that spans the subarctic region. Dense stands of larch, pine, spruce, and birch stretched for thousands of kilometers, interrupted only by rivers, marshes, and occasional clearings. The climate was extreme beyond the experience of most Europeans. Winter temperatures regularly reached -50 degrees Celsius, cold enough to freeze exposed skin in minutes. These winters lasted 6 to 8 months. Summer brought different challenges, swarms of mosquitoes and other insects in such numbers that they could suffocate small animals, and heat that could reach 30 degrees, turning the ground into impassable mud, where the permafrost melted. The Tunguska region specifically was among the most inaccessible places on Earth. Located in what is now Krasnoyarsk Krai in central Siberia, it lay nearly 4,000 kilometers from Moscow. No roads reached it. No railways connected it to civilization. The only access was by river during the brief summer months when the ice melted, or by arduous overland journey through the forest. A trip from Moscow to Tunguska could take months. The indigenous Evenki people had inhabited this region for centuries. They were semi-nomadic, following their reindeer herds and supplementing their diet with hunting and fishing. They knew the taiga intimately, understanding its rhythms and dangers in ways that outsiders never could. Their worldview was animistic, seeing spirits in natural phenomena and treating the forest with a mixture of respect and caution. Russian settlement in Siberia had begun in earnest in the 16th and 17th centuries, driven initially by the fur trade and later by agriculture and mineral extraction. But even by 1908, Russian presence in the deep taiga was minimal. A few trading posts, some Orthodox missions, and scattered villages of exiles, criminals, and old believers who had fled religious persecution comprised the Russian population. Scientific infrastructure in Russia was limited. The Imperial Academy of Sciences in St. Petersburg, founded by Peter the Great in 1724, was the primary scientific institution. It maintained observatories, libraries, and museums and supported a small number of researchers. But compared to Western European nations or the United States, Russian science operated with minimal funding and resources. Most scientists focused on practical problems: agriculture, mining, military applications. Pure research was a luxury. Astronomy and meteorology were particularly underdeveloped. Russia had few astronomical observatories, and those that existed were concentrated in the western part of the empire. Siberia had essentially no scientific infrastructure. Weather stations were rare. The vast majority of the territory was scientifically unmapped and unstudied. This was the context in which the Tunguska event occurred, an explosion of unprecedented magnitude in one of the world's most remote locations, in a country with limited scientific capacity and no systems for investigating such phenomena. The timing could hardly have been worse for scientific investigation. Russia, in 1908, was also politically unstable. The disastrous Russo-Japanese War of 1904 to 1905 had ended in humiliating defeat. The revolution of 1905 had shaken the empire, forcing the Tsar to establish a parliament and make promises of reform that many saw as inadequate. Strikes, protests, and political violence were common. The government's attention was focused on maintaining order and preventing further unrest, not on investigating mysterious explosions in Siberia. Communication technology was primitive by modern standards. The telegraph existed, but was unreliable, especially in remote regions. Telephones were rare luxuries, found only in major cities. Most information traveled at the speed of human movement, by foot, horse, or boat. This meant that news of the Tunguska explosion spread slowly and fragmentarily. Initial reports were confused and contradictory. Some witnesses spoke of an earthquake. Others described a meteor or shooting star. Still others believed a military ammunition depot had exploded. Local newspapers published brief notices, but these rarely reached the capital or international audiences. Western European observatories noted atmospheric anomalies but had no way to connect them to an event in central Siberia. The scientific understanding of cosmic impacts in 1908 was also limited. While meteorites were known and studied, large-scale impact events were considered historical curiosities. The connection between cosmic impacts and geological features like craters was not fully established. The idea that an object from space could explode in the atmosphere without leaving an obvious impact site was not yet part of scientific thinking. This combination of factors, remote location, limited scientific infrastructure, political instability, poor communications, and incomplete theoretical understanding meant that the Tunguska event initially attracted little systematic attention. It would be nearly 2 decades before anyone conducted a serious scientific investigation of the site. In the days and weeks following the explosion, fragmentary reports began to reach the outside world. The first published account appeared in the Siberian newspaper in Irkutsk, the largest city in eastern Siberia, located approximately 1,000 kilometers south of the blast site. The article, published on July 2, 1908, just 2 days after the event, described a celestial body of fiery appearance that had appeared in the northwest, followed by sounds like gunfire. The report noted that the sounds continued for 2 hours and were heard across a wide area. However, the article treated this as a curiosity rather than a major event, devoting only a few paragraphs to it. Over the following weeks, additional reports appeared in local Siberian newspapers. The accounts were inconsistent. Some described an earthquake, others spoke of a meteor. The language used was often sensational. The sky split in two. Fire rained from heaven. The earth shook as though the world was ending. These dramatic descriptions, combined with the remote location and lack of official investigation, meant that many readers dismissed the reports as exaggeration or superstition. Meanwhile, scientific observations were being made, though their significance was not yet recognized. Seismographic stations across Eurasia had recorded unusual signals. The Irkutsk Magnetic and Meteorological Observatory, about 1,000 kilometers from the impact site, registered what appeared to be an earthquake at the correct time. Similar seismic disturbances were recorded in Tashkent, Tbilisi, and Jena in Germany. More puzzling were the atmospheric observations. For several nights following July 30th, unusual luminous phenomena were observed across northern Europe and western Russia. The nights were so bright that at midnight in London, people could read newspapers outdoors without artificial light. Photographers in England were able to take pictures using only ambient light after sunset. The sky had a silvery, glowing quality, unlike normal twilight. These phenomena were noted and discussed in European scientific circles, but no one connected them to the Siberian explosion. Various explanations were proposed: unusual auroral activity, volcanic dust in the atmosphere, or effects related to solar activity. The Krakatoa volcanic eruption in 1883 had produced similar atmospheric effects, leading some scientists to speculate that another major eruption had occurred somewhere in Asia. Astronomers proposed different theories. The comet Encke had passed near Earth's orbit in June 1908. Some suggested that Earth might have passed through the comet's tail, with cosmic dust in the upper atmosphere creating the luminous nights. This theory had some merit, as cometary material can indeed cause atmospheric effects, but it didn't explain the explosion reported in Siberia. The Imperial Academy of Sciences in St. Petersburg received informal reports about the Siberian event but took no action to investigate. The location was too remote, the reports too contradictory, and the Academy's resources too limited. Moreover, Russia in 1908 faced more pressing concerns. Political tension, economic problems, and the aftermath of the failed revolution occupied the government's attention. Local authorities in Siberia conducted minimal investigation. The regional governor in Yeniseisk, the administrative center for the area, requested reports from settlements near the Tunguska River. These reports, compiled over several months, confirmed that something extraordinary had occurred. Trees had been flattened over a wide area. Forest fires had burned for weeks. But with no scientific expertise available locally and no obvious economic or security implications, the matter went no further. The Evenki people, whose territories included the blast area, developed their own interpretations. Their oral traditions incorporated the event into their cosmology. Some groups believed it was punishment from the sky god Ogdi for human transgressions. Others saw it as a battle between good and evil spirits. These interpretations, while not scientific, preserved important details about the event's effects that would later prove valuable to investigators. Some Evenki reported that their reindeer herds, which had been grazing near the blast site, were killed or scattered. Others described finding areas where the ground had been scorched and trees had fallen in strange patterns, all pointing away from a central location. These observations were consistent with a massive explosion, but without scientific investigation, their significance was not recognized. In the international scientific community, the Tunguska event remained essentially unknown. European and American scientists were aware of the unusual luminous nights in late June and early July 1908. But these were treated as a separate phenomenon from reports of an earthquake or meteorite in Siberia. The information remained fragmented, with no one connecting the atmospheric observations in Europe with the explosion in Central Asia. This situation persisted for years. World War I erupted in 1914, further diverting attention and resources. The Russian Revolution of 1917 plunged the country into civil war that lasted until 1922. During this period of chaos and violence, scientific research in Russia nearly ceased. The Imperial Academy was reorganized into the Soviet Academy of Sciences, but it operated with drastically reduced funding and capabilities. Throughout this period, the Tunguska site remained uninvestigated. The forest gradually began to recover. New growth appeared among the fallen trees. The scorched earth was slowly covered by vegetation. Without human intervention, nature was erasing the evidence of what had occurred. It was not until the mid-1920s, as the Soviet Union began to stabilize and scientific work resumed, that anyone seriously considered investigating the Tunguska event. Even then, it took a unique combination of circumstances and one determined individual to finally mount an expedition to the remote blast site. The man who would eventually solve the Tunguska mystery was Leonid Alexeyevich Kulik, born in 1883 in Tartu, then part of the Russian Empire. His path to Tunguska was shaped by both scientific curiosity and personal resilience forged through hardship. Kulik's early life was marked by intellectual ambition and practical challenges. He studied physics and mathematics at the Imperial Academy of Forestry in St. Petersburg, showing particular interest in mineralogy and geology. However, his education was interrupted by the Russo-Japanese War of 1904 to 1905. Kulik served as a soldier and was captured by Japanese forces, spending months in a prisoner-of-war camp. This experience, while undoubtedly difficult, developed in him a capacity for endurance and patience that would prove essential in his later work. After the war, Kulik struggled to establish himself. He worked as a teacher, a surveyor, and various other jobs while pursuing scientific work whenever possible. He married and started a family, adding financial pressure to his already precarious situation. Yet throughout these difficult years, he maintained his scientific interests, particularly in meteorites. In 1920, Kulik joined the Mineralogical Museum of the Soviet Academy of Sciences in Petrograd, which would later be renamed Leningrad. His position involved cataloging and studying the museum's meteorite collection. For Kulik, this was more than just a job. Meteorites represented a connection to the cosmos, physical evidence of the larger universe beyond Earth. He became convinced that studying meteorite impacts could reveal important information about Earth's history and the nature of the solar system. Kulik was methodical and obsessive in his work. Colleagues described him as a man of few words but intense focus. He could spend hours examining a single rock sample, measuring, weighing, analyzing its composition. His notebooks, which survive in the archives of the Russian Academy of Sciences, show meticulous record-keeping and careful reasoning. It was through this work that Kulik first became aware of the Tunguska event. In 1921, while reviewing old academic journals and regional archives, he discovered references to the 1908 explosion. The reports intrigued him. Witnesses described a fireball crossing the sky, followed by an enormous explosion. These were consistent with a large meteorite impact. If true, this would be one of the largest meteorite falls in recorded history. However, the reports also contained puzzling elements. No one mentioned finding meteorite fragments. There were no accounts of a crater, which a meteor large enough to cause such an explosion should have created. Some reports described the object exploding in mid-air rather than striking the ground. These details didn't fit the standard pattern of meteorite falls that Kulik had studied. Despite these inconsistencies, Kulik became convinced that Tunguska had been caused by a massive meteorite. He believed that if he could locate the impact site and recover fragments of the object, it would be a scientific discovery of enormous importance. The size of the explosion suggested a meteorite much larger than any previously studied. Such an object might contain rare minerals or provide insights into the composition of asteroids. Kulik began advocating for an expedition to investigate the site. This proved challenging. The Soviet Union in the early 1920s was still recovering from years of war and revolution. Resources were scarce, and scientific expeditions to remote areas were not a priority. Kulik's proposals were repeatedly rejected due to lack of funding. In 1921, Kulik attempted to reach Tunguska on his own, with minimal resources. He traveled by train and riverboat, getting as far as the town of Kansk, several hundred kilometers from the blast site. There, bad weather, lack of supplies, and the approaching winter forced him to turn back. He had come close, but had not reached his goal. The failure only strengthened Kulik's determination. Over the next several years, he continued to gather information about the Tunguska event, interviewing anyone who had been in the region in 1908 or had heard accounts from witnesses. He collected newspaper clippings, corresponded with local officials in Siberia, and compiled everything he could find about the explosion. Kulik also refined his theory about what had happened. He believed that a large iron meteorite, perhaps weighing thousands of tons, had struck the Earth near the Podkamennaya Tunguska River. The lack of reported fragments didn't concern him. He reasoned that the object might have buried itself deep in the ground or shattered into pieces that were scattered across a wide area. The absence of a crater was more puzzling, but he theorized that the marshy terrain might have obscured the impact site. By 1927, Kulik had accumulated enough evidence and made enough appeals that the Soviet Academy of Sciences finally approved and funded an expedition. He was given a small team, basic equipment, and enough resources for several months in the field. At age 44, after years of preparation and setbacks, Kulik would finally have his chance to investigate the greatest meteorite mystery of the age. The expedition's preparations took months. Kulik had to organize supplies for extended travel through remote wilderness, food, camping equipment, scientific instruments, photographic gear, and materials for specimen collection. He recruited assistants, though finding people willing to spend months in the Siberian taiga proved difficult. He studied maps, though accurate maps of the region barely existed, and he arranged transportation, a complex logistics challenge, given that the area had no roads and minimal river traffic. In February 1927, Kulik and his team departed from Leningrad. Their route would take them across the breadth of Russia by train to Taizhe in Siberia, then by horse and sled to the town of Kezhma on the Angara River, and finally by boat up the Podkamennaya Tunguska River to the blast site. The journey itself would prove to be an ordeal that tested even Kulik's considerable reserves of determination. The journey to Tunguska was an expedition into wilderness that few Europeans had ever penetrated. Kulik's diary, preserved in the archives of the Russian Academy of Sciences, provides a detailed account of the challenges his team faced. From Taizhe, where the Trans-Siberian Railway ended its useful trajectory for their purposes, the expedition traveled by horse-drawn sledge to Kezhma, a small settlement on the Angara River. This leg of the journey in late winter, 1927, took them through frozen forests where temperatures dropped to -40 degrees Celsius. The horses struggled through deep snow. Several times, sledges broke through ice-covered streams, requiring hours of work to extract them and dry the supplies. At Kezhma, Kulik negotiated with local officials and Evenki guides. His objective was to hire people who knew the region and could lead the expedition to the blast site. This proved more difficult than anticipated. The Evenki regarded the area as cursed or haunted. They called it Valikhata, the place of death. Animals avoided it, they said. The spirits were angry there. Trees grew strangely, if they grew at all. These warnings might have seemed like superstition to European-trained scientists, but they contained practical truth. The blast area was indeed dangerous, with unstable ground, deadfall timber, and areas where forest fires had created treacherous conditions. The Evenki's reluctance was based on genuine hazards, not just spiritual beliefs. Eventually, Kulik convinced several Evenki hunters to serve as guides, though at considerably higher pay than they had initially requested. In April, as the ice on the rivers began to break up, the expedition transferred to boats and began traveling up the Podkamennaya Tunguska River. River travel in spring Siberia was hazardous. The ice breakup created jams and flooding. The current ran fast and treacherous. Mosquitoes and other biting insects emerged in such numbers that they formed visible clouds. Kulik's diary records one day when the insects were so thick that breathing without inhaling them was difficult. The team wrapped their heads in netting, but the insects found every gap in their clothing. As they progressed upriver, the Evenki guides began pointing out changes in the forest. Trees with branches broken off, unusual patterns of deadfall, scorched bark on still-living trees. These were the outer effects of the blast, apparent dozens of kilometers from the epicenter. In late May 1927, the expedition reached the settlement of Vanava, the closest inhabited place to the blast site, located about 60 kilometers south of the epicenter. Here, Kulik interviewed elderly residents who remembered the 1908 event. Their accounts were remarkably consistent. A ball of fire had crossed the northern sky. Then came an explosion so powerful that it threw people to the ground and shattered windows. The ground shook. In the minutes following the blast, a hot wind had blown through the settlement, strong enough to strip leaves from trees. One witness, S.B. Semenov, provided particularly detailed testimony. He had been sitting on the porch of his house when the event occurred. The sky to the north had suddenly split open, and fire appeared, spreading across the horizon. The heat was so intense that he felt his shirt might catch fire. Then came a massive explosion and a shock wave that threw him several meters from where he had been sitting. Looking north, he saw a column of smoke or dust rising into the sky. These testimonies confirmed for Kulik that he was in the right area. Something catastrophic had indeed occurred, and its effects had been felt across a radius of hundreds of kilometers. From Vanavara, the expedition would need to travel overland through the taiga to reach the epicenter itself. The final leg of the journey proved the most difficult. There were no trails through the dense forest. The team had to cut their way through underbrush, cross swamps and rivers, and navigate around areas where deadfall made progress impossible. They moved slowly, making only a few kilometers per day. The horses could not navigate the terrain, so supplies had to be carried by hand or moved in small boats along creeks. Kulik's determination drove the expedition forward when others wanted to turn back. His diary entries from this period show both the physical hardship and his growing excitement. The evidence of the explosion became more apparent with each kilometer. Trees were increasingly damaged. Some stood stripped of branches, dead sentinels pointing at the sky. Others lay fallen in increasingly organized patterns. Then, on June 23, 1927, the expedition reached a vantage point that gave them their first clear view of the devastation. From a ridge, Kulik looked out over the valley of the Podkamennaya Tunguska and saw something that would haunt his memory for the rest of his life. What Kulik saw from that ridge was devastation on a scale he had never imagined. His diary entry for June 23, 1927, preserved in the Russian Academy of Sciences archives, captures his initial reaction. From the summit, I observed an amazing picture. To the north, beyond the shallow valley, in the direction of the Makirta River, at a distance of 15 to 20 kilometers, one could see the barren waste of the destroyed forest. The scale of the destruction was overwhelming. I estimated that the flattened area extended for dozens of kilometers. As the expedition descended from the ridge and entered the blast zone, the extent of the catastrophe became clearer. Millions of trees lay on the ground, all oriented outward from a central point like spokes on a wheel. The pattern was so precise that it could only have been caused by an explosion of tremendous force emanating from above. The trees themselves told a story. Those farthest from the epicenter had been knocked down, with their branches intact, falling away from the blast center. Closer to the center, trees were stripped of branches before falling. And at the very center, trees remained standing, but they were completely dead, bark scorched black, branches and foliage gone. They stood like telegraph poles, vertical corpses of what had once been a living forest. Kulik estimated the devastated area at approximately 2,000 square kilometers, an area larger than the City of London. Within this zone, virtually every tree had been affected. Some estimates placed the number of fallen trees at 80 million. The destruction extended in a butterfly-shaped pattern, suggesting that the explosion had occurred at an angle rather than directly vertical. The ground itself showed evidence of intense heat. In some areas, the soil had been baked hard. Rocks showed signs of melting. Mosses and lichens that normally covered everything in the taiga were absent in the central zone, killed by the blast and subsequent fires. Kulik and his team spent weeks exploring the devastation, taking photographs, making measurements, and collecting samples. They established a base camp and began systematic investigation of the area. Kulik's methodology was rigorous. He mapped the orientation of fallen trees, noting the precise pattern they formed. He measured the heights of remaining standing trees. He collected soil samples from various depths. And most importantly, he searched for meteorite fragments. This search was based on Kulik's fundamental assumption that a large iron meteorite had caused the destruction. Such an object should have left fragments scattered across the area. Kulik expected to find lumps of nickel iron, possibly oxidized by exposure, but still identifiable as extraterrestrial material. However, no obvious meteorite fragments were found. The team excavated numerous sites where the ground appeared disturbed. They dug into what appeared to be shallow depressions, thinking these might be small impact craters. But each excavation revealed only permafrost and bog water. No iron, no stone, nothing that appeared to be extraterrestrial material. This absence of a crater or obvious meteorite fragments was deeply puzzling. The explosion had been powerful enough to flatten thousands of square kilometers of forest. The energy required for such destruction was enormous. Where was the object that had delivered this energy? Kulik explored several hypotheses. Perhaps the main mass of the meteorite had buried itself deeply in the swampy ground, with the explosion occurring as it impacted soft earth rather than rock. Perhaps it had shattered into fragments too small to easily locate in the dense undergrowth. Or perhaps it had vaporized on impact, though this seemed unlikely for an object large enough to cause such widespread devastation. The 1927 expedition concluded in August when approaching winter and depleted supplies forced Kulik to return to civilization. He had documented the devastation thoroughly, taken extensive photographs, and collected numerous samples, but he had not found what he most wanted: physical evidence of the meteorite itself. Despite this disappointment, Kulik was more convinced than ever that Tunguska had been caused by a cosmic impact. The pattern of destruction was too systematic to be anything else. The energy released was consistent with a large meteorite, and the Evenki accounts of a fireball crossing the sky match descriptions of large meteorite falls elsewhere in the world. Upon returning to Leningrad, Kulik analyzed the samples he had collected and wrote detailed reports for the Academy of Sciences. His photographs of the devastated forest, showing millions of fallen trees radiating from a central point, were dramatic evidence of the explosion's magnitude. These images would become iconic, reproduced in scientific papers and popular accounts for decades to come. Kulik immediately began planning a return expedition. He argued that more extensive excavation was needed, particularly in the central zone, where he believed the main mass of the meteorite must be buried. He proposed bringing drilling equipment to penetrate the frozen ground more deeply, and he wanted to spend more time interviewing Evenki witnesses to establish the object's trajectory more precisely. Kulik returned to Tunguska in 1928, leading a larger and better-equipped expedition. This time, he brought drilling equipment, more sophisticated surveying instruments, and additional personnel. The Soviet Academy of Sciences, impressed by his initial findings, had allocated more substantial resources. The 1928 expedition focused on the central zone, where Kulik believed the meteorite's main mass must have impacted. He identified several areas that seemed like possible impact sites, depressions in the ground that might mark where fragments had struck. The team spent months excavating these locations, digging through permafrost and bog water. Again, they found nothing. No meteorite iron, no fusion crust, none of the characteristic features of impact sites. The depressions they had excavated appeared to be natural features of the landscape, possibly old thermokarst formations where melting permafrost had created sinkholes. This second expedition did produce new findings. Kulik conducted more extensive surveys, creating detailed maps of the fallen trees' orientations. He established that the epicenter was indeed near the Podkamennaya Tunguska River, in an area where several branches of the river created a complex drainage pattern. He also documented that the blast had triggered extensive forest fires, with charred tree trunks visible throughout the affected area. Interviews with additional Evenki witnesses provided more details about the 1908 event. Several people described seeing the fireball cross the sky from southeast to northwest. Some reported hearing thunder-like sounds continuing for several minutes after the initial explosion. Others described a black rain falling shortly after the blast, possibly ash or dust thrown into the atmosphere. These testimonies helped Kulik refine his understanding of the event's timeline. The object had apparently approached from the southeast at a relatively low angle, perhaps 30 degrees from horizontal. It had exploded in mid-air, possibly detonating before impact due to the stresses of atmospheric entry. This would explain the lack of a crater and the pattern of destruction radiating outward from a central point above the ground. However, this interpretation created new problems for Kulik's meteorite hypothesis. Iron meteorites, the type Kulik assumed had caused the explosion, were known to survive atmospheric entry relatively intact. They typically created impact craters when they hit the ground. An explosion in mid-air suggested something different, perhaps a comet rather than a metallic asteroid. Kulik rejected this possibility. Comets were thought to be relatively fragile objects, composed largely of ice and dust. While a comet might explode in the atmosphere, Kulik doubted one could generate the energy evident at Tunguska. He remained convinced that an iron meteorite was responsible, and that more extensive excavation would eventually locate it. A third expedition, in 1929 to 1930, focused on attempting to photograph the site from the air. Kulik arranged for several aerial reconnaissance flights over the blast area, producing the first aerial photographs of the devastation. These images dramatically illustrated the scale of the destruction and the precise radial pattern of fallen trees. They also confirmed that there was no obvious large crater in the area. The aerial photographs allowed more precise mapping of the blast zone. Kulik identified the exact epicenter, a point roughly 8 kilometers above the ground where the explosion had occurred. From this point, the blast wave had spread outward in all directions, with the force concentrated along certain directions due to the angle of the explosion. The 1929 to 1930 expedition also conducted more sophisticated scientific measurements. Magnetic surveys were performed to detect any buried iron masses. Soil samples were analyzed more carefully for trace elements that might indicate extraterrestrial material. Tree ring analysis was attempted on surviving trees to look for evidence of the blast's effects on growth patterns. These studies produced mixed results. Some soil samples showed elevated levels of nickel and iridium, elements common in meteorites but rare in terrestrial rocks. However, the concentrations were too low to be conclusive. The magnetic surveys detected no large iron masses buried in the ground. Tree ring analysis showed that surviving trees had experienced a growth spurt in the years following 1908, likely due to reduced competition after so many trees had fallen. But this didn't help identify the cause of the explosion. By the early 1930s, Kulik had spent years investigating Tunguska and had established several important facts. The explosion had occurred approximately 8 kilometers above the ground. It had released energy equivalent to 10 to 15 megatons of TNT. The blast pattern was consistent with a mid-air detonation, and no large meteorite crater or obvious meteorite fragments had been found. These findings were published in Soviet scientific journals and gradually became known internationally. The Tunguska event began attracting attention from scientists in other countries. Astronomers, in particular, were intrigued. The idea of a large cosmic object exploding in Earth's atmosphere was unprecedented in recorded history. However, the lack of definitive physical evidence meant that the cause remained debatable. Kulik continued to maintain that a meteorite was responsible, but other scientists proposed alternatives. Some suggested that a small comet had exploded in the atmosphere. Others proposed that a cloud of cosmic dust had been compressed by Earth's magnetic field, creating an explosion. A few even suggested that the event might have been caused by some form of matter-antimatter annihilation, though this idea was considered highly speculative. Kulik planned further expeditions, but political and economic factors intervened. The Soviet Union, in the 1930s, was undergoing forced industrialization and collectivization. Resources for pure scientific research were increasingly scarce. Kulik struggled to obtain funding for additional trips to Tunguska. The outbreak of World War II in 1939 disrupted scientific research throughout Europe and the Soviet Union. Many scientists were mobilized for military service or directed toward research with military applications. Kulik himself was called to serve, despite being nearly 60 years old. In 1941, when Nazi Germany invaded the Soviet Union, Kulik volunteered for military service. He joined a Home Guard unit defending Moscow as German forces advanced toward the capital. His age and scientific credentials could have exempted him from combat duty, but Kulik insisted on serving. Colleagues who knew him described this decision as characteristic: stubborn determination, bordering on obsession, whether in scientific research or in defending his country. In October 1941, Kulik's unit was surrounded by German forces near Mozhaisk, west of Moscow. He was wounded and captured. The conditions in German prisoner of war camps on the Eastern Front were notoriously brutal. Soviet prisoners received minimal food, inadequate shelter, and essentially no medical care. Mortality rates were catastrophic. Leonid Kulik died in a German POW camp in April 1942, likely from dysentery combined with complications from his wounds and general malnutrition. He was 58 years old. The man who had survived hardships in the Siberian taiga, who had devoted years to solving the Tunguska mystery, died in captivity before seeing his theories validated. Kulik's death represented a significant loss to Soviet science. His meticulous documentation of the Tunguska site, his careful collection of samples, and his persistent investigation over more than a decade had established the foundation for all future research. Without his work, the event might have remained nothing more than local legend, uninvestigated and unexplained. However, Kulik's legacy survived in his detailed journals, photographs, maps, and collected samples. These materials were preserved by the Soviet Academy of Sciences, where they would prove invaluable to later researchers. His photographs of the devastated forest, in particular, became iconic images, showing millions of fallen trees radiating from a central point with eerie precision. During the war years, the Tunguska site was essentially forgotten. The Soviet Union was fighting for survival against Nazi invasion. Scientific expeditions to remote Siberia were impossible. The mystery of what had happened in 1908 was set aside as the nation focused on more immediate threats. The war's conclusion in 1945 brought new scientific awareness. The atomic bombings of Hiroshima and Nagasaki had demonstrated the devastating power of nuclear explosions. Photographs of blast damage from these cities bore striking resemblance to Kulik's photographs from Tunguska. Buildings or trees flattened in radial patterns, objects at the epicenter left standing but severely damaged. This similarity prompted new interest in Tunguska. Scientists who had studied the effects of nuclear explosions recognized similar patterns in Kulik's documentation. The implication was profound. The Tunguska explosion had released energy comparable to a large nuclear weapon, but decades before, nuclear technology existed. In the late 1940s and 1950s, Soviet scientists began returning to Tunguska with new questions and new analytical techniques. They were no longer simply searching for meteorite fragments. They were investigating the physics of massive atmospheric explosions and their effects on the environment. The resumption of Tunguska research in the late 1940s occurred in a dramatically different scientific and political context. The Soviet Union was now a superpower, locked in Cold War competition with the United States. Nuclear weapons and their effects were matters of urgent military and scientific interest. Any natural phenomenon that produced nuclear-scale destruction warranted careful study. Kirill Florensky, a young geochemist at the Soviet Academy of Sciences, led expeditions to Tunguska in 1958 and 1961. These expeditions were far better equipped than Kulik's had been. They included geologists, physicists, chemists, and botanists, each bringing specialized expertise. They had improved surveying equipment, better analytical instruments, and helicopters that could access the remote site more easily than the river and overland routes Kulik had used. Florensky's team approached the investigation systematically. Rather than searching for a large meteorite mass, they looked for microscopic evidence of extraterrestrial material. They collected soil samples from various depths and locations, water samples from streams and bogs, and samples of tree wood and bark from both the blast zone and control areas outside it. Back in laboratories in Moscow, These samples were analyzed using techniques unavailable in Kulik's time. Spectrographic analysis could detect trace elements at parts per million concentrations. Microscopic examination revealed tiny spherules, microscopic balls of melted rock and metal that had cooled in the air. These spherules were crucial evidence. Analysis showed they contained nickel, iron, cobalt, and other elements in ratios typical of meteoritic material but different from terrestrial rocks. The spherules were found in soil layers corresponding to 1908, and their distribution pattern centered on the blast area. This was the physical evidence Kulik had sought but never found. The meteorite had not survived intact, nor had it left large fragments. Instead, it had completely vaporized in the atmosphere, leaving only a microscopic trace. Millions of tiny droplets of melted material that had scattered across hundreds of square kilometers and settled into the soil. Vasily Fast, working with Florensky's team, conducted extensive surveys of tree damage patterns. By examining the orientation and type of damage to trees at different distances from the epicenter, Fast could model the blast wave's characteristics. The data indicated an explosion approximately 8 kilometers above the ground, with energy release of 10 to 15 megatons. The pattern of damage also revealed details about the explosion itself. Trees directly beneath the blast point remained standing, but were stripped of branches and bark, killed by the thermal pulse. Trees farther out were knocked down by the blast wave, but the direction of fall indicated the explosion had occurred above, rather than on the ground. The precision of the radial pattern demonstrated that this was a single explosion, not multiple impacts. In 1960, a Soviet physicist named Kirill Stanyukovich proposed a comprehensive theory. Based on the evidence accumulated by Florensky and others, Stanyukovich argued that Tunguska had been caused by a small asteroid or comet nucleus that exploded in the atmosphere. The object, perhaps 50 to 80 meters in diameter, had been traveling at cosmic velocity when it encountered Earth's atmosphere. At such speeds, approximately 27,000 kilometers per hour or more, the atmospheric resistance generates tremendous heat and pressure. The object would have begun to ablate, lose material from its surface, almost immediately upon entering the denser lower atmosphere. As it descended, the combination of aerodynamic stress and heating increased until the object's structural integrity failed catastrophically. The resulting explosion released the kinetic energy of the object's motion essentially instantaneously. This energy, equivalent to 10 to 15 megatons of TNT, was deposited in the atmosphere at an altitude of approximately 8 kilometers. The blast wave propagated outward from this point, devastating the forest below. The explosion also vaporized the object itself, along with any solid fragments that might have survived the initial breakup. This explained the absence of a crater and the lack of large meteorite fragments. The microscopic spherules found by Florensky's team represented the only physical remnant, condensed droplets of material that had been vaporized and then re-solidified as they cooled in the air. This explanation, known as the atmospheric explosion or airburst hypothesis, gradually gained acceptance in the scientific community. It explained all the major features of the Tunguska event: the massive energy release, the mid-air explosion, the radial damage pattern, the absence of a crater, and the presence of microscopic extraterrestrial material in the soil. However, significant questions remained. What exactly was the object? An asteroid or a comet? How common were such events? Could they be predicted or prevented? And most concerning, what would happen if a similar object exploded over a populated area rather than remote Siberian forest? During the Cold War, the Tunguska event acquired additional significance beyond pure scientific interest. Both the Soviet Union and the United States were developing increasingly powerful nuclear weapons and studying their effects. Tunguska represented a natural analogue to a nuclear airburst, the type of detonation that military strategists considered most effective for destroying cities. Soviet military scientists visited the Tunguska site to study the effects of the blast wave on structures, in this case trees rather than buildings. But the physics were similar. They wanted to understand how energy from a high-altitude explosion propagated to the ground and what patterns of damage resulted. This information could help in both designing nuclear weapons and developing civil defense measures. The KGB, the Soviet security agency, classified some aspects of Tunguska research. Reports that contained detailed analysis of blast effects or discussion of how to detect and track incoming objects were deemed sensitive. The concern was that such information might help adversaries understand Soviet capabilities or vulnerabilities. This classification had the paradoxical effect of feeding conspiracy theories. Secrecy surrounding a mysterious explosion naturally prompted speculation. Some Westerners wondered if Tunguska had actually been a secret Soviet nuclear test, though this was chronologically impossible given that the event occurred in 1908, decades before nuclear technology existed. Others suggested that the Soviets had recovered alien technology from the site and were keeping it secret. These speculations were nonsense, but they persisted because genuine scientific information was difficult to obtain. Soviet scientists published some findings in domestic journals, but language barriers and Cold War restrictions limited international access. Western scientists relied on summaries and translations, often incomplete. The situation improved somewhat in the 1960s and 1970s as scientific cooperation increased despite political tensions. International conferences on cosmic impacts and planetary defense began to include both Soviet and Western scientists. Tunguska became a topic of shared interest, recognized as important for understanding impact hazards regardless of political systems. Carl Sagan, the American astronomer and science communicator, wrote extensively about Tunguska in his popular works. He described it as the clearest warning the universe has sent to modern civilization about the reality of cosmic threats. Sagan used Tunguska to argue for international cooperation in detecting and potentially deflecting dangerous asteroids and comets. Arthur C. Clarke, the British science fiction author and futurist, also referenced Tunguska frequently. In his novel Rendezvous with Rama, Clarke imagined a future where humanity had created a comprehensive spacewatch system to detect incoming objects, motivated partly by studying historical impacts like Tunguska. Clarke called it proof that the universe is not as benign as we'd like to believe. NASA and the European Space Agency, ESA, became interested in Tunguska as they developed programs to track near-Earth objects, NEOS. Astronomers recognized that asteroids and comets regularly crossed Earth's orbit, and that impacts, while rare on human timescales, were inevitable over geological time. Tunguska demonstrated that even relatively small objects, tens of meters in diameter, could cause regional-scale catastrophe if they hit the wrong place. The Chicxulub crater discovery in 1980, evidence of the asteroid impact that ended the dinosaur era 66 million years ago, provided cosmic context. Impacts had shaped Earth's biological history. Mass extinctions, climate shifts, and evolutionary pressures had resulted from objects falling from space. Tunguska was simply the most recent significant example in a long history of cosmic bombardment. By the 1980s, the scientific consensus on Tunguska was essentially established. An asteroid or comet nucleus, approximately 50 to 80 meters in diameter, had exploded in the atmosphere over Siberia on July 30th, 1908. The explosion had released 10 to 15 megatons of energy, devastating over 2,000 square kilometers of forest, but leaving no crater. Microscopic traces of extraterrestrial material remained in the soil, but the object itself had been completely vaporized. This understanding, built on Kulik's foundational work and refined by decades of subsequent research, closed the scientific mystery while opening new questions about planetary defense and the ongoing threat from space. 21st century research has added precision and detail to our understanding of the Tunguska event, using technologies and analytical methods unavailable to earlier investigators. Computer modeling, satellite imagery, advanced materials analysis, and sophisticated physics simulations have all contributed to a more complete picture. One significant advance has been computational modeling of atmospheric explosions. Scientists can now simulate what happens when a large object enters Earth's atmosphere at cosmic velocity. These simulations incorporate realistic physics, aerodynamic heating, mechanical stress, fragmentation dynamics, and energy deposition in the atmosphere. The models show that objects in the 50 to 80 meter size range, depending on composition and entry angle, will typically disintegrate at altitudes of 5 to 15 kilometers. The breakup is violent, occurring over a few seconds as the object is subjected to forces it cannot withstand. The fragments continue moving forward briefly before exploding as their kinetic energy is converted to heat and blast wave. For Tunguska specifically, the best-fit models suggest an object approximately 60 meters in diameter, entering at about 27,000 kilometers per hour at an angle of roughly 30 degrees from horizontal. The object was likely stony rather than metallic, possibly a fragment of an asteroid or potentially a comet nucleus, though distinguishing between these possibilities remains difficult. The explosion occurred at approximately 8 kilometers altitude, above a point near 60.9 degrees north, 101.9 degrees east, close to the Podkamennaya Tunguska River. The energy release was approximately 15 megatons. The blast wave propagated outward, flattening trees in a pattern that computational models can now accurately reproduce. These simulations explain several previously puzzling features. The butterfly-shaped pattern of destruction, rather than a perfect circle, results from the object's angled trajectory. Trees directly beneath the explosion remained standing because the blast wave was vertical at that point, pushing straight down rather than sideways. The most severe damage occurred where the blast wave struck the ground at an angle, imparting horizontal force sufficient to snap tree trunks. Modern analysis of tree rings from surviving trees has provided additional information. Trees within the blast zone, but not killed outright, show growth anomalies corresponding to 1908. Some show scarring from fire damage. Others show growth rings that indicate the tree was blown partially over but survived. The pattern of these effects can be mapped to reconstruct the blast's characteristics. Soil analysis using modern techniques has confirmed and extended Florensky's findings. Microscopic particles of melted rock and metal, chemically distinct from terrestrial material, are present in soil layers corresponding to 1908. The distribution of these particles centers on the blast area and extends outward for dozens of kilometers. This is exactly what would be expected from an object that vaporized in the atmosphere, with the resulting cloud of material settling back to Earth. One ongoing debate concerns whether any fragments of the object survived to reach the ground. In 2007, an Italian team, led by Luca Gasparini, proposed that Lake Checo, a small lake about 8 kilometers from the epicenter, might be an impact crater from a surviving fragment. The lake has an unusual funnel shape, and sediment analysis showed it might be relatively young. However, Russian scientists disputed this interpretation. Additional studies suggested Lake Checo predates 1908 and is a natural feature rather than an impact crater. Seismic surveys of the lake bottom found no evidence of the fractured rock that would be expected beneath an impact crater. The debate continues, but the majority view is that Lake Checo is not impact-related. The trajectory of the object has been reconstructed using the pattern of tree falls, eyewitness accounts, and seismic records. Multiple analyses converge on a path from southeast to northwest, entering the atmosphere over Mongolia and exploding over the Tunguska River Valley. The precise trajectory matters for determining where the object came from and whether similar objects might pose future threats. Some researchers have attempted to identify the parent body. If Tunguska was an asteroid fragment, it came from the asteroid belt between Mars and Jupiter. If it was a comet, it likely originated from the outer solar system. Analysis of the entry trajectory and date suggests possible association with the Beta Taurid meteor stream, a debris field associated with Comet Encke. However, this connection remains speculative. The timing of the impact, late June by the modern calendar, mid-July by the Julian calendar still in use in Russia in 1908, coincides with Earth's passage through several meteor streams. This has led some researchers to propose that Tunguska was related to normal meteor shower activity, just an unusually large fragment. Others argue the timing is coincidental. What is certain is that objects of Tunguska size are relatively common in near-Earth space. Current estimates suggest approximately 300,000 objects larger than 40 meters diameter exist in near-Earth orbits. Of these, fewer than 1% have been detected and catalogued. Most are too small and dark to be easily observed with current telescopes. The frequency of Tunguska-scale events is estimated at roughly once per century, on average. This doesn't mean they occur exactly once per 100 years, but rather that the statistical probability of such an impact is approximately 1% per year. The events are random, and the next one could occur tomorrow or not for several centuries. What has changed since 1908 is the consequence of such an event. The Tunguska explosion devastated remote forest where essentially no humans lived. A similar explosion over a populated area would be catastrophic. A 15-megaton blast over a city would cause casualties comparable to a nuclear attack. This sobering reality has driven development of programs to detect and potentially deflect threatening objects. To understand Tunguska's significance, it helps to compare it with other documented impact events and to place it within the broader spectrum of cosmic threats Earth faces. At the small end of the spectrum are the meteors visible on any clear night. These are typically pebble-sized or smaller, burning up harmlessly in the upper atmosphere. Slightly larger objects, basketball-sized rocks, produce brilliant fireballs that occasionally drop small meteorites to the ground. These events occur daily somewhere on Earth, but usually go unnoticed because most of Earth's surface is ocean or uninhabited land. Moving up in scale, objects a few meters across produce notable atmospheric entries. One such event occurred over Caracas, Peru, in September 2007. An object estimated at 3 to 4 meters diameter survived atmospheric entry and impacted the ground, creating a crater 13 meters across. The impact caused no casualties, but did produce minor injuries from flying debris and possibly noxious gases released from underground water deposits. This event was significant as one of the few recent, well-documented cases of a small asteroid creating a crater. The Sikhote-Alin meteorite fall in February 1947, also in Russia, represented a different type of event. An iron meteoroid, estimated at approximately 90 metric tons, broke apart in the atmosphere over the Sikhote-Alin Mountains in eastern Siberia. The fragments that reached the ground created numerous craters, the largest about 26 meters across. This fall was witnessed and carefully documented by Soviet scientists, providing valuable data about how iron meteoroids behave during atmospheric entry. Both Caracas and Sikhote-Alin were smaller than Tunguska. The objects were small enough that fragments survived to impact the ground, creating craters. Tunguska represented a different phenomenon, an object large enough to carry enormous energy but composed of material that couldn't survive the stresses of atmospheric entry at high speed. The next recorded event in Tunguska's magnitude range occurred on February 15, 2013, over Chelyabinsk, Russia. This event provided dramatic modern documentation of an atmospheric explosion similar to, but smaller than Tunguska. The Chelyabinsk meteor was estimated at approximately 20 meters diameter, about one-third the size of the Tunguska object. It entered Earth's atmosphere at about 18 kilometers per second, slower than typical asteroid velocities. The object fragmented and exploded at an altitude of about 30 kilometers, releasing energy estimated at 400 to 500 kilotons, roughly equivalent to 20 to 30 times the Hiroshima bomb. Despite occurring at much higher altitude than Tunguska, the Chelyabinsk explosion caused significant effects. The blast wave shattered windows across a wide area, with broken glass causing more than 1,500 injuries, mostly minor cuts. The event was captured on numerous dashboard cameras, security cameras, and smartphones, providing unprecedented documentation of a large meteor's atmospheric entry and explosion. Analysis of Chelyabinsk footage allowed scientists to reconstruct the event in detail. The object's trajectory, velocity, composition, and explosion dynamics were all determined more precisely than for any previous impact event. This data validated theoretical models of atmospheric explosions and provided a calibration point for understanding Tunguska. The comparison is instructive. Chelyabinsk, at roughly one-third Tunguska's size, exploded at 30 kilometers altitude and broke thousands of windows. Tunguska, 3 times larger, exploded at 8 kilometers altitude and devastated 2,000 square kilometers of forest. The inverse relationship between explosion altitude and ground damage is clear. Lower explosions are far more destructive. Scaling up from Tunguska leads to truly catastrophic scenarios. The Barringer crater in Arizona, also known as Meteor Crater, was formed approximately 50,000 years ago by an iron meteorite roughly 50 meters in diameter. Unlike Tunguska, this object was dense enough to survive atmospheric entry largely intact, impacting the ground at high velocity. The resulting crater is 1.2 kilometers across and 170 meters deep. The explosion was estimated at 10 megatons, similar to Tunguska, but the ground impact concentrated the energy differently. Moving further up the scale, we reach the Chicxulub impact of 66 million years ago. The asteroid that created this crater, located beneath Mexico's Yucatan Peninsula, was approximately 10 kilometers in diameter. The impact released energy estimated at 100 million megatons, roughly 10 million times more powerful than Tunguska. The environmental effects included global wildfires, a dust cloud that blocked sunlight for years, acid rain, and climate changes that led to the extinction of non-avian dinosaurs and approximately 75% of all species on Earth. Fortunately, Chicxulub-scale impacts are extremely rare, occurring on average once every 100 million years or so. Tunguska-scale events are far more common, but still infrequent enough that human civilization had never documented one before 1908. The frequency of impacts follows a rough power law. Smaller objects hit more often, larger objects less frequently. Objects the size of the Chelyabinsk meteor, about 20 meters, impact Earth approximately once every 60 years on average. Tunguska-size objects, 50 to 80 meters, hit roughly once per few centuries. Objects large enough to cause global catastrophe, 1 kilometer and larger, impact once every few 100,000 to million years. These are statistical averages, not predictions. The randomness of cosmic impacts means that multiple large impacts could occur in rapid succession, or long intervals could pass with no significant impacts at all. The key point is that impacts are ongoing phenomena, not simply historical curiosities. This realization, driven largely by studying Tunguska, has motivated the development of programs to detect potentially hazardous objects and eventually to develop methods of deflecting them. The recognition that impacts like Tunguska pose an ongoing threat has led to the development of planetary defense systems designed to detect and potentially deflect dangerous objects. This field, which barely existed before the 1990s, has become a significant area of space science and policy. The foundation of planetary defense is detection. You cannot defend against a threat you don't know exists. Beginning in the 1990s, systematic surveys of near-Earth objects, NEOs, were established, primarily by NASA, but with participation from other space agencies and observatories worldwide. The SpaceGuard survey, initiated after a 1992 U.S. congressional mandate, aimed to detect 90% of NEOs larger than 1 kilometer diameter within 10 years. This goal was later expanded and refined, with current objectives including cataloging 90% of NEOs larger than 140 meters. The 140-meter threshold was chosen because objects this size or larger could cause regional devastation if they impacted Earth. Multiple ground-based telescope systems contribute to NEO detection. The Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, in Hawaii, the Catalina Sky Survey in Arizona, and the Asteroid Terrestrial Impact Last Alert System, ATLAS, also in Hawaii, continuously scan the sky for moving objects. These systems have dramatically increased the rate of asteroid discovery. As of 2024, approximately 33,000 NEOs have been catalogued, with several hundred new discoveries each month. The vast majority are small objects that pose no threat, but occasional discoveries reveal objects that pass uncomfortably close to Earth. The definition of uncomfortably close in astronomical terms is typically within a few lunar distances, about 1 million kilometers. One concern is that current detection systems have blind spots. Objects approaching from certain directions, particularly from sunward, are difficult or impossible to detect with ground-based telescopes because they're hidden in the sun's glare. The Chelyabinsk meteor approached from this direction, which partly explains why it wasn't detected before impact despite being a relatively large object. This limitation has motivated proposals for space-based detection systems. A telescope positioned in Venus orbit or at the L1 Lagrange point between Earth and Sun would have an unobstructed view of objects approaching from sunward. NASA's NEO Surveyor mission, currently in development, aims to provide this capability. Detection is only the first step. Once a potentially hazardous object is identified, its orbit must be determined precisely. This requires multiple observations over time, allowing astronomers to calculate the object's trajectory and predict future positions. For most NEOs, these calculations quickly rule out any impact threat. The object's orbit clearly misses Earth by comfortable margins for centuries into the future. Occasionally, however, calculations reveal a non-zero probability of future impact. These cases trigger additional observations and more refined calculations. As more data is collected, the uncertainty typically decreases, usually resolving to show that no impact will occur. The object will pass close to Earth, perhaps very close in astronomical terms, but miss. The concerning scenario is when additional observations fail to rule out impact, instead confirming that a collision is likely or certain. This has never occurred with adequate warning time, but it's the scenario for which planetary defense systems are being developed. If a threatening object is detected with years or decades of warning, deflection might be possible. The key is changing the object's velocity by even a small amount, perhaps a few centimeters per second, years before the predicted impact. This tiny velocity change, applied years in advance, can result in the object missing Earth by thousands of kilometers. Several deflection methods have been proposed and studied. The most developed concept is the kinetic impactor, essentially ramming the asteroid with a spacecraft at high velocity. The collision transfers momentum, slightly altering the asteroid's orbit. The amount of deflection depends on the spacecraft's mass and velocity, the asteroid's mass, and various details about how energy is transferred during impact. In September 2022, NASA's Double Asteroid Redirection Test (DART) mission successfully demonstrated this technique. DART deliberately crashed into Dimorphos, a small moon orbiting the asteroid Didymos. Neither object threatened Earth. This was purely a test. The impact changed Dimorphos's orbital period around Didymos by 32 minutes, far more than the predicted minimum of 73 seconds needed to declare the test successful. DART proved that kinetic impact deflection works. A spacecraft can be navigated to hit a small asteroid with precision, and the impact can measurably change the asteroid's motion. This was a milestone in planetary defense, moving the concept from theoretical possibility to demonstrated capability. Other deflection methods remain theoretical, but could be important for certain scenarios. A gravity tractor involves positioning a spacecraft near an asteroid for an extended period, using the spacecraft's gravitational attraction to gradually pull the asteroid into a different orbit. This method is slow but very precise and could be useful for delicate situations. Nuclear explosive deflection has been studied as a method for larger or more imminent threats. A nuclear device detonated near, not on, an asteroid could vaporize surface material, creating thrust that pushes the asteroid away. This method is controversial due to concerns about nuclear weapons in space, but it might be the only option for certain large and fast scenarios. For very small asteroids, where the warning time is short but the threat is limited to local areas, evacuation might be the best response. An object the size of Chelyabinsk, detected a few days before impact with a predicted impact location, doesn't require deflection. Evacuating the area and warning people to stay away from windows would prevent casualties. The challenge is that most objects in the Tunguska size range remain undetected. Current surveys focus on larger objects, which are easier to see and pose greater threat, but are also rarer. Smaller objects like Tunguska are more common but harder to detect. Many will remain undiscovered until detection technology improves. This gap in detection capability is sometimes called the Chelyabinsk problem. Objects large enough to cause regional damage, but small enough to be hard to detect, represent an ongoing threat that current systems cannot fully address. Improving this situation requires better telescopes, space-based detection systems, and more comprehensive sky surveys. International cooperation has improved in recent years. The United Nations has established an international asteroid warning network to share information about potential threats. Space agencies from multiple countries participate in planetary defense research. The issue transcends national boundaries. An impact anywhere affects the entire planet to some degree. However, significant challenges remain. Detection systems are incomplete. Deflection capabilities have been demonstrated only at small scale. Decision-making processes for potential deflection missions, particularly those involving international cooperation and possible use of nuclear devices, are not fully established. And the fundamental randomness of impacts means that a large, dangerous object could be discovered tomorrow with inadequate warning time to respond. Tunguska serves as both warning and motivation. It demonstrated that cosmic impacts are not merely historical phenomena, but ongoing threats. It showed that even relatively small objects can cause regional catastrophe, and it occurred in a remote area where casualties were minimal. A similar explosion over a populated region would be one of the worst natural disasters in recorded history. More than a century after the explosion, the Tunguska site has physically recovered, but its historical and scientific significance remains. In 1996, the Russian government established the State Nature Reserve Tunguska Event Site to protect the area and facilitate continued research. The reserve covers approximately 296,562 hectares of taiga forest centered on the epicenter of the 1908 explosion. Access is restricted and requires special permits, partly to protect the environment and partly because the remote location makes it dangerous for unprepared visitors. The forest has regenerated. Younger trees now cover the landscape where millions of their predecessors fell in 1908. However, evidence of the explosion remains visible to trained observers. Charred stumps from the original forest still exist beneath the soil. Tree ring analysis of surviving trees shows the growth anomalies corresponding to 1908, and the distribution of tree ages reveals the pattern of destruction and subsequent regeneration. The soil still contains the microscopic spherules identified by Florensky's expeditions. These tiny particles of melted extraterrestrial material mixed with terrestrial soil provide ongoing research material. Modern analytical techniques can extract more information from these samples than was possible in earlier decades. Scientific expeditions continue to visit the site, though much less frequently than during the peak research period of the 1960s through 1980s. Current research focuses on long-term ecological effects, refined analysis of existing samples using improved techniques, and ground truth testing of computer models of atmospheric explosions. The nearest significant settlement is Vanavara, about 60 kilometers south of the epicenter. This small village, with a population of a few hundred, serves as the access point for researchers visiting the site. In Vanavara, a small museum documents the event and the history of its investigation. The museum contains artifacts from early expeditions, photographs by Kulik and later researchers, samples of affected trees, and exhibits explaining the science of atmospheric explosions. Elderly residents of Vanavara sometimes share family stories about the event, passed down through generations. While no one currently alive witnessed the 1908 explosion directly, Oral traditions preserve accounts from witnesses who described their experiences to children and grandchildren. These stories, while not scientifically precise, maintain cultural memory of the event. Tourism to the site is limited but growing. Each year, a few dozen adventurous travelers make the difficult journey to Vanavara and arrange guided trips to the epicenter area. The journey requires several days of hiking through roadless wilderness, usually supported by local Evenki guides who know the terrain. For those who complete the journey, standing at the epicenter of the Tunguska explosion provides a powerful connection to this pivotal moment in humanity's understanding of cosmic threats. The cultural legacy of Tunguska extends far beyond the site itself. The event has inspired numerous works of fiction, from science fiction stories exploring alternative explanations to historical novels dramatizing Kulik's expeditions. The mystery of Tunguska has appealed to storytellers because it combines scientific investigation, remote wilderness, and a phenomenon that was initially inexplicable. Some fictional treatments have promoted pseudo-scientific explanations that Tunguska was caused by an alien spacecraft crash, or an antimatter explosion, or a black hole passing through Earth, or a secret weapons test. These explanations are scientifically implausible and contradicted by evidence, but they persist in popular culture because they're more dramatic than the actual explanation. The scientific community has worked to counter these pseudo-scientific narratives while acknowledging the legitimate mystery that Tunguska represented before the evidence accumulated. The progression from mystery to understanding demonstrates the scientific process: initial observations, hypothesis formation, evidence collection, theory refinement, and eventual consensus. Tunguska appears in educational materials as a case study in multiple contexts. For planetary science, it illustrates atmospheric explosions and impact phenomena. For environmental science, it demonstrates ecosystem responses to catastrophic disturbance. For history of science, it shows how investigations can span decades and require multiple research teams before resolution. And for planetary defense, it serves as the clearest historical example of the threat that near-Earth objects pose. The event also raises philosophical questions about chance and consequences. The Tunguska object could have exploded anywhere on Earth. That it did so over remote Siberian forest, where virtually no humans lived, was purely random. Had it arrived a few hours earlier or later, Earth's rotation would have placed a different location beneath its trajectory. Moscow, St. Petersburg, London, or other major cities could have been in its path. This randomness is uncomfortable. Human psychology tends to seek patterns and purpose in events, but cosmic impacts are genuinely random. The next Tunguska-scale event could occur over empty ocean, where it would pass almost unnoticed, or over a major city, where it would cause catastrophic casualties. There is no way to predict the location, only the statistical frequency. This reality has motivated the planetary defense efforts described earlier. For perhaps the first time in human history, we have the potential technological capability to detect and possibly deflect threatening objects. Whether we will develop and deploy these capabilities adequately before they're needed remains uncertain. The Tunguska event stands as one of the most significant natural phenomena in recorded history, not despite, but because of where and when it occurred. An explosion of nuclear magnitude in one of Earth's most remote locations, at a time when scientific investigation was difficult but just barely possible, provided humanity with a clear warning about cosmic threats while minimizing immediate casualties. The lessons from Tunguska are multiple and profound. First, space is not empty and benign. Millions of asteroids and comets populate the solar system, many in orbits that cross Earth's path. Most are small, posing no threat beyond spectacular meteor displays. But some are large enough to cause regional or even global catastrophe if they impact. These objects exist. They are real, and Earth's eventual encounter with more of them is certain. Second, the threat is not merely theoretical. Tunguska proved that large atmospheric explosions actually occur in human history, not just geological deep time. The event was witnessed, documented, and investigated. The evidence is concrete. Another impact of similar or greater magnitude will eventually occur. The only questions are when and where. Third, the scale of destruction from relatively small cosmic objects is sobering. The Tunguska impactor was modest by astronomical standards, perhaps 60 meters across, a fragment of rock or ice insignificant in the context of the solar system. Yet it released energy equivalent to hundreds of Hiroshima bombs and devastated an area larger than a major metropolitan region. Objects of this size are relatively common in near-Earth space. Current estimates suggest hundreds of thousands exist, and fewer than 1% have been detected. Fourth, timing and location matter enormously. The same explosion that flattened remote forest would have killed hundreds of thousands or millions if it had occurred over a city. Moscow, with approximately 1 million inhabitants in 1908, could have been completely destroyed if Earth's rotation had placed it beneath the Tunguska trajectory. The randomness of the event's location was, from a human perspective, extraordinarily fortunate. Fifth, atmospheric explosions leave different evidence than ground impacts. The absence of a crater at Tunguska initially complicated the investigation, but it ultimately revealed important physics. Not all cosmic impacts create craters. Objects of certain sizes and compositions explode in the atmosphere, releasing their energy without leaving obvious surface scars. This means that historical impacts might have gone unrecognized because investigators were looking for craters rather than patterns of destruction consistent with airburst explosions. Sixth, scientific investigation of rare phenomena requires patience and persistence. Leonid Kulik devoted years to investigating Tunguska, facing skepticism, limited resources, and harsh conditions. He died before his theories were fully validated. Yet his meticulous documentation enabled later scientists to build on his work. The resolution of the Tunguska mystery required decades and contributions from multiple research teams using progressively improving technology. Seventh, international cooperation on planetary defense serves everyone's interest. Cosmic impacts don't respect national boundaries. An asteroid impact anywhere has global implications, whether through direct effects or through economic and political disruption. Detecting and deflecting threats requires sharing data, coordinating observations, and potentially collaborating on deflection missions. The United Nations frameworks for asteroid warning and response represent important steps, but further development is needed. Detection is achievable, but incomplete. Current telescope surveys have identified most of the largest near-Earth asteroids, those that could cause global catastrophe. But smaller objects, still capable of causing regional devastation, remain largely undetected. Improving detection capabilities, particularly for objects approaching from sunward, requires ongoing investment in ground-based and space-based observatories. Ninth, deflection is possible, but requires adequate warning time. The DART mission demonstrated that kinetic impact deflection works. A spacecraft can hit an asteroid and change its orbit measurably, but this technique requires years or decades of warning to be effective. An object detected weeks before impact cannot be deflected with current technology. This makes comprehensive detection systems essential. They provide the warning time that makes deflection possible. 10th, the absence of recent major impacts has created complacency. Human civilization has never experienced a Tunguska-scale event over a populated area. The largest recent impact, Chelyabinsk, caused property damage and injuries, but no deaths. This fortunate history can create the mistaken impression that the threat is minimal or theoretical. Tunguska reminds us that absence of recent catastrophe does not mean absence of threat. The event also provides perspective on humanity's place in the cosmos. For most of human history, celestial events were interpreted through religious or supernatural frameworks. Comets were omens, meteors were signs from gods, and the idea that rocks falling from space could reshape civilization was not part of cultural consciousness. Tunguska occurred at a pivotal moment when scientific thinking was becoming dominant but was not yet universal. The Evenki witnesses interpreted the event through their traditional cosmology as action by sky spirits. Russian scientists recognized it as a natural phenomenon requiring investigation. The tension between these worldviews, both present in the historical record, illustrates the transition from traditional to scientific understanding of the universe. Today, we understand Tunguska as a natural consequence of Earth's existence in a solar system containing millions of asteroids and comets. Some of these objects have orbits that cross Earth's path. Occasionally, purely by chance, Earth and object arrive at the same point in space at the same time. The result is an impact, with consequences ranging from a pretty meteor to global catastrophe depending on the object's size. This understanding demystifies cosmic impacts while making them more concerning. They're not divine punishment or supernatural events. They're physics. A massive object moving at tremendous velocity carries kinetic energy. When that energy is released, through atmospheric explosion or ground impact, the effects follow predictable physical laws. The equations that describe these phenomena are well understood. The challenge is detection and response, not comprehension. The modern study of near-Earth objects and development of planetary defense systems represents humanity's first serious attempt to protect itself from a class of threat that has shaped Earth's history for billions of years. Impacts have caused mass extinctions, altered climate, and influenced evolution. Until recently, they were simply acts of nature that life on Earth endured. Now, potentially, they're risks that can be managed. Whether this capability will develop adequately before it's needed is uncertain. Comprehensive detection systems remain incomplete. Deflection capabilities have been demonstrated only at small scale. International cooperation frameworks exist, but are not fully tested, and the political will to invest substantially in planetary defense competes with more immediate concerns. Tunguska provides both warning and motivation. It demonstrates that the threat is real, that impacts causing regional devastation occur on timescales of centuries rather than millions of years, and that such events can happen with no warning. It also demonstrates that scientific investigation can resolve initially mysterious phenomena, and that understanding leads to the possibility of protection. The forest that was devastated on July 30th, 1908, has regrown. Trees once again cover the landscape. Animals have returned. The ecosystem has recovered. But the lesson remains: the universe is not a safe place, and Earth exists in an environment where catastrophe can arrive without warning from a clear sky. More than a century after that summer morning, when the Tiger exploded, we have the knowledge to understand what happened and the beginning of capability to prevent similar events from causing catastrophe. Whether we will use that capability wisely, investing adequately in detection and deflection before the next major impact occurs, remains one of the defining questions of our era. The sky above Tunguska is clear and quiet now, as it was on the morning of July 29, 1908, hours before the explosion. Somewhere in that sky, unseen and untracked, other objects follow their orbits through the solar system. Some will never come near Earth. Others will pass close, but miss, and some, inevitably, will arrive. The question is whether we will see them coming and whether we will be prepared to respond. The answers we provide to these questions may determine whether future generations remember our era as the time when humanity became mature enough to protect itself from cosmic threats, or as the civilization that understood the danger but failed to act before it was too late. Tunguska was a warning written in fallen trees and scorched earth. The message was clear to those willing to read it. What remains to be seen is whether humanity will heed the warning or wait until a similar explosion occurs not over remote forest but over one of our cities, transforming a scientific curiosity into one of history's greatest catastrophes. The silence of the Siberian forest is deceptive. It suggests that the danger has passed, that what happened in 1908 was an isolated event unlikely to recur. But the silence is only local and temporary. The cosmos continues its dance, indifferent to human concerns. Objects continue to orbit, cross paths, and occasionally intersect with Earth. We now have eyes to see these objects and potentially hands to push them aside. Whether we will prove wise enough to use these capabilities before they're desperately needed is a test that humanity has never before faced. Tunguska provided the examination question. Our response, as a technological civilization capable of affecting its own cosmic environment, will determine whether we pass or fail. The story of Tunguska is ultimately a story about transition, from a humanity at the mercy of cosmic forces to one that might, with sufficient foresight and effort, protect itself. It's a story about the power of scientific investigation to resolve mysteries and the importance of learning from near catastrophes. And it's a story that remains unfinished because the threat that Tunguska revealed continues, and our response to that threat is still being written. Thanks for watching. See you in our next documentary.